Welcome to This Explainer. Today, we are cracking open a genuinely fascinating document, the highly technical operating manual of a literal mechanical titan. The machine we're looking at is the Plasser India BA 093X. It's this massive, incredibly complex piece of railway maintenance machinery that basically keeps our trains running safely. We're going to use this manual to decode exactly how this beast wakes up and gets to work. Let's dive right in. If you've ever wondered how heavy infrastructure equipment transforms from a dormant transport vehicle rolling down the rails into a highly tuned working powerhouse, well, this source document literally holds the blueprints. Our goal today is to translate this dense technical manual to understand the exact anatomy of that transformation. Here is how we will break it down. 1. Waking up the machine. 2. Preparing the track tools. 3. The hydraulic muscle. And 4. The pneumatic lungs. All right, section 1, waking up the machine, from travel mode to work mode. So when this multi-ton machine arrives at a work site, it doesn't just instantly start bending steel, right? To move from its standard travel load to an active work mode, the manual lays out this strictly choreographed step-by-step awakening protocol. First, the driving gearbox has to be switched to neutral. Then, parking brakes are applied. Only after the safety circuit is confirmed clear is the second engine started. And finally, the main working switch is thrown. It's a highly calculated sequence designed entirely to make sure this thing doesn't accidentally trigger its massive tools during transport. It's kind of like watching a heartbeat spike as it wakes up. We start at a standard idling pulse of 900 RPM, but the second you hit that main working switch, the automated system jumps to an increased idle of 1400 RPM. Then, when the operator fully dials it in, Engine 1 roars to a working speed of 1890 RPM, while Engine 2 holds steady at 1800. You can literally trace the power surging through the system. Now, the manual actually drops this intense all-caps warning right here. Do not step into the danger zone any longer. The instant that working system start switch is depressed, a warning horn blasts and flashing lights near the tamping units go off on both sides. It's essentially a mechanical roar, letting everyone nearby know that the Titan's automated systems are now dangerously alive. Moving on to Section 2, preparing the track tools, extending the appendages. Okay, so the core engines are running, and the beast is fully awake. It's time to prep the tools. But before I can flex any of that heavy equipment, there's a critical safety rule detailed in the manual. All safety ropes and chains securing the measuring trolleys absolutely must be loosened before they can be lowered. In fact, to unlock them, the document states the trolleys first have to be slightly lifted by switching over pneumatic valves, just to relieve the pressure on the locking mechanism. It's a really delicate but necessary operation before the heavy work begins. Once those are unlocked, the operator hits a central switch to drop a complex array of precision sensors right onto the tracks. Mapped out before us is a system that includes the front tension trolley, the lining trolley, the middle leveling feeler rod, and the rear tension trolley. Once they're lowered, horizontal and vertical datum pressure is automatically applied. This forces these sensitive trolleys to perfectly hug the reference rail so they can map the track's exact alignment. And this mapping is absolutely crucial. It's what ensures passenger and freight trains don't derail at high speeds. Depending on the specific mission, the machine actually physically shifts between two primary working modes. In sleeper-to-sleeper mode, it drives from one railway tie to the next, and its satellite unit remains firmly locked in place. But in continuous work mode, that satellite is unlocked. This allows it to shift laterally, centering the tamping units over the rails and working smoothly while the main machine continuously rolls forward. But here's the thing. Dropping sensors onto a rail is one thing, right? Actually shifting, bending, and lifting massive steel railway tracks requires a staggering amount of force. So how does this machine generate that invisible, immense power required for the job? Well, that brings us straight to its internal anatomy. Let's find out in Section 3, the hydraulic muscle, fluid power dynamics. This is all about the fluid power dynamics that give the machine its brute strength. The raw physical power of the BA093X comes from an intricate hydraulic system fed by 6 fixed displacement pumps mounted on the gearbox. Think of these as the Titan's heart, pumping hydraulic lifeblood throughout the whole machine. Interestingly, the manual points out a critical protective measure here. During cold starts, at temperatures of 5 degrees Celsius or lower, the gear must be disengaged. The pumps actually have to be operated without any load or pressure until the engine warms up, just to make sure this vital system isn't damaged. Looking at these pressure thresholds is absolutely wild. The general working system operates at 140 bar. The tamping system, which handles the squeezing cylinders, requires 150 bar. But the vibratory drive, which literally shakes and forces the heavy track ballast stone into place beneath the rails, demands a massive 185 bar of pressure. To put that into perspective for you, that is roughly equivalent to the crushing water pressure you'd feel almost 2 kilometers deep in the ocean. And all of that force is focused on packing stone beneath a rail to provide a rock-solid foundation. Now, to ensure a perfectly smooth, constant delivery of oil pressure for all those high-powered squeezing functions, the machine relies on a specialized hydraulic accumulator. And inside that accumulator, exactly 85 bar of tightly stored energy, waiting like a coiled spring, ready to be unleashed. To maintain that incredible 85 bar of stored energy safely, the document throws down another really stark mandate. Only nitrogen may be used for all compressed oil containers. Using everyday compressed air in these hydraulic accumulators would be totally ineffective and, frankly, extremely dangerous. So pure nitrogen is a vital ingredient for the machine's muscular stability. Which brings us to Section 4, the pneumatic lungs, the nervous system. So while hydraulics provide the brute force, the machine still needs a way to control those movements with high precision. That's where the compressed air system comes in, basically acting as the machine's breath and nervous system. But this air has to be perfectly conditioned. The manual details a rigorous 4-step purification process. First off, air compressors on the engines supply the air. Second, a water separator removes the initial moisture. Third, an air dryer uses a granulate to further dehumidify the system. And finally, a pneumatic oiler adds just a precise, economical amount of lubrication to ensure the internal valves never seize up. So why go through all that trouble for some air? Well, because it controls the machine's absolute most vital split-second reflexes. This conditioned air is responsible for stretching the delicate lining and leveling cords, locking and unlocking those heavy measuring trolleys, controlling the hydraulic working brakes, operating the heavy tamping unit locks, and even triggering that massive pneumatic warning horn we talked about earlier. Because this breathing system handles literally everything from precision track alignment to life-saving emergency braking, the manual lays out a very strict maintenance mandate. These pneumatic containers act as vital reservoirs, and they must be regularly drained by actuating a drainage valve to get rid of any collected moisture. If the machine is stopped for a long period, they have to be completely drained. For the Titan to survive and function safely, this simple act of exhaling is absolutely non-negotiable. And that brings us to a much bigger question to close things out today. By decoding just this one operating manual, we've seen exactly how beautifully choreographed these complex systems are, how the hydraulic muscles and pneumatic lungs have to work in perfect, albeit dangerous, harmony. So if a single document reveals this much hidden, specialized complexity just to maintain our railway tracks, what other mechanical titans are out there, invisibly shaping the infrastructure we rely on every single day? It's definitely something to think about the next time you're riding a train. Thanks so much for joining me on this explainer. I really hope you found decoding this manual as fascinating as I did.